Hey guys, today we're going to be going over acid-base reactions. Most of this is actually going to be stuff that you're already familiar with. Some of these reactions will be ones that we've already talked about earlier this semester. Others will be ones that we've talked about last year, but let's get into it. So acid-base reactions are just any reactions that involve an acid or a base or both. We're going to be talking about dissociation and ionization reactions again, so just a little bit of review of that. You also do want to make sure that you know whether or not an acid or a base will ionize or dissociate. We are going to talk about acid rain, so that's not super important for you guys to know at this point. And then we are going to be talking about neutralization reactions, and you will have to be able to write neutralization reactions on your own given just the name of the acid and base. So that means predicting the products and writing the formulas of all of them, as well as balancing. So originally, Arrhenius said that all acids and bases will dissociate in solution. He said that acids would dissociate to produce hydrogen ions, also called protons, and bases would dissociate to produce hydroxide ions. We now know that that's not the case. Acids do not dissociate, and not all bases do. Only bases that are also ionic compounds, which are our bases that have an OH in them, actually dissociate. So for example, at the bottom there, we have NaOH, sodium hydroxide, which is also an ionic compound because Na is a metal and O and H are nonmetals. Because it's an ionic compound, it will dissociate, which means just break apart into its two ions. So we'll get our metal ion, which is Na+, and we'll get our hydroxide ion, which is OH-. These bases will always dissociate to produce OH-. Ionization for acids and bases is sometimes referred to as the modified Arrhenius equation or Bronsted-Lowry equation. Essentially, according to the modified Arrhenius, all acids as well as weak bases will ionize in aqueous solution or in water. Acid and bases will always react with the water and end up producing two ions. One of the ions produced by an acid will always be hydronium or H3O+, and bases will always produce OH-, and that just comes from whether or not they are proton donors or proton acceptors. An acid will donate or give a proton to the water, which is where the H3O+ comes from. With a base, the base is a proton acceptor and will actually steal a proton from the water, which is what then turns into the OH-. And we have some examples of those down at the bottom. Again, we've already done this, but hydrochloric acid will react with water to produce a hydronium ion. And then to figure out what the other ion is when an acid ionizes, you just take the H off the front of the acid, and whatever's left becomes your other ion. If we're doing this with a base, the base will react with the water to produce hydroxide. To figure out what the other ion is, we just add an H+ to our base. And remember, ammonia, NH3, is a base. So acid rain is any type of precipitation caused by the burning of fossil fuels. It can be either wet or dry. Wet deposition is when you have acids with a pH below 5.6 falling to the ground as precipitation. That could be rain, snow, fog, etc. Dry deposition is when you have sulfates or nitrates or even carbon dioxide becoming acidic solutions when they come into water that's already on Earth's surface. So right here, between a pH of about 1 and 5 is where we have acid rain. As soon as you have acid rain cause a drop in pH in lakes of even a drop to like from say neutral to 5, it's going to affect the reproduction of fish, so they might not be able to have offspring anymore. And then if you drop another scale on the pH, it'll actually start to kill the adult fish. So acid rain is formed when the emissions from burning fossil fuels mix with either oxygen, ozone, and or water to form nitric acid and sulfuric acid. Carbon dioxide can also react with water to produce acidic solutions, and then this acid can fall to Earth's surface in the form of precipitation. Due to eastern moving weather patterns, most places on the eastern side of North America are affected more than places on the western side. And that's just because our jet stream moves from west to east, our prevailing winds move from west to east. So it kind of pushes all of that pollution eastwards. So the way that acid rain is formed with just carbon dioxide is carbon dioxide will react with 2 water molecules to produce a hydronium ion and an HCO3 minus. And then that ion can also act as an acid in solution. So that's where our acid rain comes from. And then both sulfates and nitrates can also react with water to produce sulfuric acid and nitric acid. So there's a lot of different impacts of acid rain. It can decrease biodiversity, it can kill off fish and decrease their populations, it can kill off insects and weeds, which fish feed on. It can kill off microbes that are in the soil, and so they don't function as well anymore. If you don't have the right microbes in your soil, it'll shut down some of your nutrient cycles, like the nitrogen cycle, for instance, so plants won't be able to get as much nutrients from the soil. The acid rain can also directly dissolve nutrients that are in the soil, and it also allows more toxins to move through the soil into the plants. Trees can also take in the toxins from the soil, which can either kill the tree itself or just make it less healthy. Acid rain in the form of like mist or fog can break down the leaves, which means that the plant's unable to photosynthesize as well, which is especially damaging to high altitude forests that have a lot of mist and fog around them. Evergreen trees become cold intolerant and die off during the winter if they're exposed to too much acid rain. You can add lime and some fertilizers to reduce the impact of acid rain. The lime can actually neutralize some of the acid, but that's not really feasible in like a huge forest area. So that's just kind of what it could look like. Human health is not directly impacted by acid rain, thankfully, though the compounds that make acid rain are also harmful to humans and can cause respiratory problems. So the main way to decrease acid rain is to just reduce air pollution, either by using alternative energy sources or conserving energy. In smokestacks, if you wash the sulfur from the smoke before it leaves the smokestack, or remove the sulfur from coal before you burn it. Stuff like that can reduce acid rain. Making sure that vehicles pass emissions tests can reduce the amount of pollution that they're putting out. Acid rain has been on the decline in Canada following the Canada-wide acid rain strategy and clean air agreement between Canada and the US, because a lot of our pollution was coming from the US. So this just kind of shows how much acid rain was happening over time. So back in the early 90s, there was really high levels of acid rain in kind of the northeastern part of the United States and like southern Ontario. Now it has decreased quite a bit, mostly because of decreased pollution coming from the US. Oopsies. About 90% of the acid rain in Eastern Canada is caused by emissions in the US Midwest. And again, just the prevailing winds carry that to us. 150 lakes in Eastern Canada are considered dead because of their acidity, and 48,000 more are at risk due to acid rain. So once they're dead, they can no longer support aquatic life because the acidity is too high. So there would be no fish and no plants or anything like that. In some areas, there is actually 40% more acid rain than normal rain. Again, the eastern provinces are more affected, and that's not only because of the wind patterns like the jet stream and the prevailing wind, but also because of differences in soil. Soil in the western provinces tends to be more alkaline or basic, which means that any acid rain that does fall tends to be neutralized. Soils in the east tend to be less alkaline, they tend to be more neutral, and therefore cannot neutralize the acid rain as effectively. Limestone, which you find more of in the west, is really basic and therefore really good at neutralizing the acid rain. Granite, which you have more of out here, not useful for neutralizing acid rain. And this chart just kind of shows where those different soils are. So if we look in Alberta here, there's a lot of carbonate bedrock, which is like limestone and stuff that is basic and really good at neutralizing acid. And that's true through most of Alberta, as well as kind of the bottom half of Saskatchewan and Manitoba. If you look at, say, Quebec and central Ontario, as well as most of the Atlantic provinces, there's very little limestone and stuff like that. It is much more granite. Okay, and then the last type of reaction that we're going to talk about is neutralization reactions, which you did learn about in Science 10. This is a special type of double displacement that occurs between an acid and a base. So the reactants do always have to be an acid and a base. Water is not a reactant. The products will always be water and then some type of salt, which is an ionic compound. The salts produced will be dependent on what ions were in the original acid and base. In these reactions, the acid will always lose a hydrogen, the base will always lose a hydroxide, and then the hydroxide and hydrogen combine to form the water. Anything that's left over forms the salt. So for example, if you have an acid in solution, again, it is going to ionize. You have the base in solution, it will dissociate if it's an ionic base like this. And then the H3O plus and OH minus are where the water comes from. The Na plus and Cl minus are where the other compound comes from, so the salt. Okay, so that's just what that is talking about. Our hydronium and hydroxide making the water, our salt forming from the other ions. In order for acids and bases to react in a neutralization reaction like this, the number of hydronium ions and the number of hydroxide ions must be the same in order for them to actually make a neutral substance. So every single hydronium ion must bind to a hydroxide ion so that all you have left is water and salt. So as long as your acid and base are the same strength, then as long as you use the same amount of both of those, they will fully neutralize each other. If, for instance, your acid is stronger, you will need more of the base in order to neutralize the acid, and then vice versa. So whichever one is weaker, you'll need more of it in order to neutralize the stronger one. And that all comes down to percent ionization. Again, the stronger one will ionize or break apart more, meaning it produces more of the either hydroxide or hydronium ion, And so you will need more of the one that ionizes less so that you can produce enough either hydronium or hydroxide ion to cancel it out. We can usually tell that a solution is being neutralized either with the use of indicators or with signs of a reaction like bubbles forming. Okay, I'm just going to go over a couple examples of writing neutralization reactions. And that's it. Okay, so for the first example here, we have hydrosulfuric acid reacting with aluminum hydroxide. So obviously our first step is to write out our formulas for our acid and base. Hydrosulfuric acid, this hydro tells us that we are not dealing with a polyatomic acid, it's just one of the normal ones. So hydro tells us there's an H, sulfuric tells us there's an S, and then we cross our charges and get H2S. Aluminum hydroxide, aluminum is Al, hydroxide is OH. And then we have to cross our charges. Aluminum has a charge of 3. Don't forget it has to go outside the brackets. And then because we have an acid and a base, we know that this is a neutralization reaction and therefore will make water. And then to figure out what the salt is going to be, I'm going to take the H's off of my acid and the OH's off of my base. Whatever's left becomes my salt. We always write metal first and then non-metal, so I will write my aluminum first and then my sulfur. And then because this is an ionic compound, I do have to cross my charges. So I should get Al2S3. Then of course I have to balance this. So I'm going to put a 2 here because I have 2 aluminum. I'm going to put a 3 here because I have 3 sulfur. And then right now I have 6 hydrogen on my acid. I have 2 times 3 is 6 hydroxide on my base, which means that I need 6 water molecules. And that is the easiest way to balance it. So start with your salt and making sure that it's balanced on the reactant side, and then your amount of hydrogen has to equal the amount of hydroxide, has to equal the amount of water. Okay, I'm going to give you guys a couple to try on your own, and then I'll give you the answers afterwards. Okay, so try these 2 examples here. Example 2, nitric acid reacting with calcium hydroxide. And then the third example, phosphorus acid reacting with lithium hydroxide. See if you can write out and balance those neutralization reactions. Okay, so this is the correct answers. So you should have 2HNO3 plus CaOH2 becomes 2H2O plus CaNO3 2. So nitric acid, because there is no hydro on the front of it, and yet it is a traditional name because it's got the word acid at the back. Because of that lack of the word hydro, I know that it is polyatomic. Nitric is our normal state polyatomic ion for nitrogen. So I look at my CBINS CP and I see that my normal state nitrate will have a charge of 1 and 3 oxygen. So I write in my 3 oxygen, and then when I cross my charges, I don't bother writing in my 1s. Calcium hydroxide, calcium has a charge of 2, so we cross it over. Water is formed because it always is in a neutralization. And then to figure out what my salt is going to be, I take the OH off my base, the H off my acid, whatever is left becomes my salt, and I write my metal out first and then my non-metal. So that is why we have calcium nitrate. And then once again, we cross our charges. So calcium has a charge of 2. I do have to put my nitrate in brackets to show that that 2 goes to the entire nitrate. And then nitrate has a charge of -1, which I don't bother writing in. And then for phosphorus acid, again, the acid tells us it's a traditional name. The lack of hydro tells us that it is a polyatomic acid. And then the ending of OUS tells us that we're dealing with a phosphite ion instead of a phosphate. So phosphite, meaning that it has 1 less oxygen than normal. So if we look at our CBIN-CP, we can see that phosphate normally has a charge of -3, and that is not going to change, but it normally has 4 oxygens. So if it was phosphoric acid, it would be H3PO4. Phosphorus acid is H3PO3. It's down an oxygen. I'm then going to react it with my lithium hydroxide. Both of those have charges of 1. Sorry, by the way, for this acid, this 3 is coming from the charge of our phosphite ion. And then we make a water because it's a neutralization reaction. And then my salt is whatever I have when I take away my OH and my H's. So I have my PO3, my phosphite ion, and my Li, my lithium ion. We put the metal first, so lithium phosphite, and then we cross our charges. Lithium has a charge of 1, so I don't have to bother writing that in. Phosphite has a charge of 3, so that is a 3 in there. Okay, you will have some more practice questions of this coming up before your quiz, but let me know if there's any questions.